So Paul, are you happy to get started?
Yes.
Yeah. Okay. So welcome to probably the last for this year in this series of Dark Energy in a Dark Age. It is my pleasure to introduce Professor Paul Shapiro from the University of Texas at Austin. Paul, thank you very much.
Thank you very much, and thank you for inviting me. This is a special experience, this long distance colloquium. I was just saying hello to Hae-Sung Kang, with whom I reminisced about the last time I was in Korea in 2002. Also had a chance to visit Pohang, actually, for my first visit. I look forward to the next. So I was going to tell you today about the Cosmic Dawn, or CoDa for short, project, and how we simulate reionization and galaxy formation. And I have a long list of collaborators I won't even take the time to mention, except some of them are Korean, like Kyunjin An and Hyunbae Park. Let me tell you that the heart of the matter is going to be addressing this big computational problem, filling in the gap in the first billion years of cosmic time by fully coupled radiation hydrodynamic simulations. And that is a challenge that I will talk about. So for those of you who are physicists and may not appreciate what we mean by the epoch of reionization, let me just say a few very basic things. The absorption spectra of quasars have long shown that the intergalactic medium at redshifts between us and a redshift of 6 are highly ionized, with a residual neutral H atom concentration of less than 1 atom in 10,000. And we know also that the universe must have experienced an epoch of reionization before this, since it ended the first few 100,000 years after the Big Bang in a nearly featureless distribution of atoms of hydrogen and helium that recombined. And in the meantime, the Sloan Digital Sky Survey of quasars was the first to observe quasars at redshifts greater than 6, whose absorption spectra showed dramatic increase in the hydrogen neutral fraction at this epoch as we look back in time. So we also know that the epoch of reionization only just ended at a redshift of about 6. So here is a famous plot from Fan et al. In 2006 showing individual quasar absorption spectra, where you can, by the way, if someone could tell me if you see my cursor.
Yes, we can see your cursor.
Great.
It is visible on the screen.
That will be my pointer. So on each of these, I have to be a little bit careful because if I touch it too vigorously, it moves the slide forward. But here you would see the rest frame Lyman alpha emission line of the quasars. And as you move to the blue, shorter wavelengths, the radiation that was en route from the quasar would have had the chance to redshift into the local atomic line center of the Lyman alpha line of the hydrogen atoms intervening so that they could scatter it. Most of them are sitting in the ground state and they simply absorb a photon, excite them to the n = 2 state. The photon is about 10 electron volts, and they then de-excite and send it off in a random direction. So when we look at the quasar, we see it as an absorption trough or an absorption feature. I'm not doing very well keeping track of my cursor. I don't know why. So forgive me if I don't have good luck with that. This now has been extended to redshifts, quasars discovered even at redshifts greater than 7, all the way up to 7.5. And the trend continues as the Lyman alpha line of the quasar is ever more redshifted. And what the important thing is that the amount of transmission drops. So when we plot the transmission through the intergalactic gas as a function of the redshift at which that transmission takes place, we see that it's plummeting as the redshift approaches 6. So we believe the IgM is becoming more neutral there and that reionization is just ending. And this too has been extended now to redshifts well beyond 6, to redshifts above 7. And the trend remains. I just should point out, in case anyone is puzzled, that the residual neutral fraction in the ionized plasma left over after the universe reionized is a sufficient, even if it's a fraction like 10 to the minus 4 or 10 to the minus 5, it's still sufficient for us to observe Lyman alpha scattering. And the difference between seeing an absorption spectrum with some transmission and an absorption spectrum through which there was no transmission is the difference between reionized and ionized. It's not fully transparent even after it's ionized. In the meantime, the Planck satellite has mapped the pattern of polarization of the cosmic microwave background radiation across the sky. Light was scattered as it traveled across the universe by intergalactic electrons released by the process of reionization. So this is a secondary source of fluctuations in the Planck polarization. And here you see a map which is filtered on the scale of 5 degrees. And when it's filtered on such large angles, the power spectrum reveals the presence of this secondary scattering layer and is therefore able to diagnose how many electrons there were en route between us and the surface of last scattering released by reionization. In particular, Planck finds that almost 6% of the CMB photons were scattered by free electrons in the intergalactic medium en route to us, but only 4% of that could have been scattered by the, I mean to say only 4% could have been scattered by the IgM at redshifts below 6. So the IgM must have been ionized earlier than a redshift 6 to supply enough electron scattering optical depth. And therefore reionization, though it may have ended around 6, was already substantial by redshifts between 8 and 10. So my job is then to theoretically model this in enough detail to capture all the important physics and make observable predictions with it so that we can learn about this last phase of the cosmological evolution of the universe accessible to direct observation. So that's the nature of the CoDa project. And what I'm showing you here, I will show you again, is a pseudo light cone or of the look back, or I should say a pseudo look back plot, where starting on the left at a redshift of about 150, the universe was filled with linear density fluctuations and mostly neutral intergalactic medium. We call that the Dark Ages. By a redshift of 20, the growth of those fluctuations produced the first stars in small galaxies, and they began to form stars inside the galaxies. The starlight leaked out into the intergalactic space between them and began to ionize it between a redshift of 20 and a redshift of 6, galaxies grow and merge, becoming increasingly nonlinear. The structure becomes increasingly nonlinear. The cosmic web takes shape. H2 regions grow and begin to overlap. And by a redshift of 6, the IgM was mostly ionized as we move to the right on this diagram. What did the ionizing? Well, the ionization was, we believe, dominated by starlight from galactic halos. And they come in 3 mass flavors, which have different contributions and different responses to the evolution of the universe. So I divide them into those groups. That's an important thing I will come to. What I'm showing you here is a plot of the abundance of the halos, the halo mass function, how many halos there are per unit volume, per unit mass interval of halo mass. And this is based upon simulations of the n-body dynamics without the radiation hydrodynamics, but the dark matter dominates the halos, and this would look very similar if I showed it to you based upon the radiation hydrodynamics. So we've simulated this over a full mass range from the genes mass subject in the baryonic component to back reaction of gas pressure, preventing the baryons from falling into the dark matter dominated halos, which we call the genes mass, from its value before the epoch of reionization, when it was down around 10,000 solar masses, to the largest halos that formed during the epoch of reionization, up above 10 to the 12th solar masses. And we've divided this into the three ranges of halo mass. The two categories that are characterized by gas whose virial temperature in equilibrium in the halos, in the absence of radiative cooling, would correspond to a sound speed that was like the orbital motions of the dark matter, also in equilibrium, in virial equilibrium in those halos. And if that velocity corresponds to a gas temperature of more than 10,000 degrees, those halos are able to cool the gas by exciting atomic hydrogen transitions down to the point of cooling to 10,000 degrees. And if they compress as they cool and lose gas pressure support, they can cool and compress all the way to making self-gravitating gas clouds in the interstellar medium of those galaxies, which can then form stars, which release UV starlight that can ionize gas. And we call those atomic cooling halos, ACHs for short. And we divide those into two groups. The halos, which are between 10 to the 8th and 10 to the 9th solar masses, are actually fragile in the presence of the ionizing radiation that sweeps through the intergalactic medium to ionize it, and also from supernova explosions that occur inside these halos when they form stars that evolve to explode. And the radiative feedback of that ionizing radiation can deprive them of fuel from the intergalactic gas so that they don't get their share of fuel to replenish the interstellar medium, and they stop forming stars if they are surrounded by ionized gas. The higher mass, above 10 to the 9th solar masses, we call high mass atomic cooling halos, HMOCs for short. They are massive enough that they can pull the baryonic gas in from the intergalactic medium to fuel that star formation, even if it's been photoheated and photoionized by reionization. So they are immune to that suppression effect, more or less. And then below the mass range of the atomic cooling halos are molecular cooling halos that can only cool gas if they are able to form hydrogen molecules, something that my former colleague and student Haesung Kang and I described in great detail as the result of processes that take ionized primordial gas and allow hydrogen molecules to form in it, which are then able to excite rotational vibrational levels that allow collisional excitation cooling and allow the gas in the mini halos, in this case, whose mass is below 10 to the 8th solar masses, to form stars when their gas becomes self-gravitating. And they too are fragile, something which I also studied in some detail some years ago with another former student and colleague, Kyunjin An, and what we know is that those halos can be evaporated by the background radiation, as we have also more recently calculated with radiation hydrodynamics in 3 dimensions by Hyunbae Park. So I've now mentioned my beloved Korean colleagues, and now let me move on. By combining the techniques of n-body dynamics that could form all of these halos and the evolving inhomogeneous density field of the intergalactic gas, without the back reaction of radiative processes or hydrodynamics, and then post-processing that with detailed treatment of the ionization and radiative transfer of the ionizing gas, we were able to perform a series of simulations of the patchy growth of reionization from the neutral intergalactic medium until the patches, the H2 regions within which the gas was ionized, grew to overlap and finish reionizing the universe. And here I show you an animation of that, where the orange regions are the ionization, are the ionized region, the blue dots are individual galactic halo sources of the ionization, and where we have introduced in this early work the process of self-regulation of reionization, in which the Jeans mass filtering of low mass source halos, the ones that are the LMOCs below 10 to the 9th, prevents them from forming stars if they are finding themselves inside one of the orange patches. We did this in a simulation that was able to resolve the formation of all of the atomic cooling halos in that volume. I will not say more until the end of my talk, if I have time, about further resolution to see if we could take account of the formation of even the mini halos. And the reason I can spend most of the talk not talking about the mini halos, I will say at the beginning, is that the same radiation that is coming out of the stars inside these early galaxies has both ionizing radiation above 13.6 electron volts, but it also has radiation between 11 and 13.6 electron volts in the so-called Lyman-Werner bands of the hydrogen molecule, which are capable of dissociating the hydrogen molecules by exciting them to electronic transitions, which then result in dissociating the molecule and decaying. And the amount and the distance, the amount of that radiation in the Lyman-Werner bands and the distance that one can see if one is an atom or a molecule in the intergalactic medium to the horizon of beyond which you cannot see more of that radiation are much larger than for the ionizing radiation. So the first thing that happens is that the release of starlight builds up the Lyman-Werner background to the point of dissociating the molecules that are there, long before it builds up the ionizing background to finish reionization. So the mini halos will contribute to reionization, but they tend to contribute only about 10% of the effect. And for the rest of my story, until I come back to it at the end, we will ignore them. Now, this n-body plus radiative transfer combo was pushed through various generations of codes and computers all the way up to several hundred megaparsec volumes. And it did get pushed in the direction of accommodating the mini halos, which I will say only something about at the end. But it did not have hydrodynamical back reaction. And so the idea of the importance of self-regulating of the reionization was a subgrid prescription, a recipe that we added, and hoped someday that simulations of this would be able to prove it and take it into account for real. And that is the story I'm going to tell for the rest of my talk. Now, in the meantime, although with these large volume simulations, we were able to make a host of predictions of observable consequences of reionization that included taking proper statistical account of the fluctuating density field, the fluctuating source field, and the inhomogeneity of reionization in space and time, the patchiness, for its effect on things like the predictions of a 21 centimeter background from the neutral atoms as they are gradually eaten away by reionization, as well as the anisotropies introduced in the cosmic microwave background by the free electrons and their motions with respect to pure Hubble expansion, which we call the kinetic Sunyaev-Zeldovich effect, and other things they contributed to radiation backgrounds. But at the same time, that self-regulation also has been thought to have a very important consequence for rescuing the underlying dark matter model that we have all invested so much in as the standard model involving cold dark matter. Cold dark matter has had a well-known problem for many years, which is that those n-body simulations that are capable of resolving the interiors of the cold dark matter halos find that the merger process of building larger halos by merging smaller halos does not destroy the smaller halos. And it destroys some of them, but it leaves a large portion of them undestroyed as serving as subhalos within the parent halo. And as galaxies, we would think of them as dwarf galaxies, which are satellites within the host more massive galaxy. And when these early predictions of how many there would be were turned to compare to the observations of the local group, including the Milky Way and M31, it was found that the observations of only of order 50 satellite dwarf galaxies were grossly undercounting the n-body results in which 1,000 Milky Way subhalos were predicted. So this has been called the missing satellites problem, and it has more subtle description I'm going to leave out. But for the longest time, a very strong element in allowing us to reconcile the cold dark matter model has been by making the overabundance of dwarf satellites essentially invisible to us by suppressing the star formation in the many of them, and at the lowest mass end especially, by exposing them to the ionizing radiation during reionization before they had a chance to make enough stars or to continue to make stars so as to be visible to us today. And so I am also going to tell you that while I won't dwell much on the results for the local group, we decided that if we were going to do this problem right, we wanted not only to simulate the back reaction of radiation and hydrodynamics on the reionization process and on the galaxies at high redshift, but also to determine what the imprint of that process was going to be on the local group, and not only an analog of the local group, such as one might have found anywhere in the universe, but actually a facsimile of the local group by making our random Gaussian noise initial conditions selected to be intentionally designed to reproduce the velocity field and the major structures and the cosmic web of the local universe itself, so that it would serve two purposes at once. It would be large enough to be like an average patch of the universe, but this average patch of the universe would be special because when we entered this patch, we would recognize our own local universe. And when we ran the simulations following reionization all the way down to redshift 0, we would see the Milky Way and M31, and we would be able to judge what the history of the reionization of the local group was. So at the same time, we were modeling the reionization of the local universe. And we get both for the price of one. So now I'm going to tell you, without dwelling on too many details, because I really have many results I'd like to share in giving you the story of what happens. And I'd rather focus on that. But in order to do this, it was necessary for my collaborators, principally Roman Tessier and Dominique Aubert, and more recently, Pierre Oswerk and their students and postdocs, but primarily those three, to develop a new code, which is a hybrid of two codes. On the galaxy formation and gravity side, with hydrodynamics and gravitational dynamics, it takes advantage of the development of the Ramses code by Tessier and his collaborators. And for radiative transfer and the ionization non-equilibrium of the hydrogen and the to respond to the ionizing radiation, it uses a code developed by Tessier and Aubert called ATON, but which Aubert transformed into a code that would be massively paralleled on a hybrid CPU-GPU architecture, which I'm going to tell you about in a moment. But first, I have to tell you why this is necessary. There are timescales in this problem, which are wildly disjoint. The hydrodynamics takes place moving gas with pressure forces on a time scale which corresponds to the sound speed of the gas. The gravitational dynamics, which moves the dark matter into the cosmic web and makes it collapse into galactic halos, and then within those halos combines the baryonic gas into interstellar clouds within which stars can form, acts on a freefall time, which is characterized by the local density we need to follow. Well, the gravitational dynamics and the hydrodynamics are not so disjoint because the hydrodynamics pulls cold gas in, shock heats it up to a temperature where the sound speed makes the sound crossing time of the object comparable to its gravitational dynamics time. But when we introduce radiative transfer and ionizing radiation, we break apart the comparability, because we introduce the physics of ionization fronts, and ionization fronts are the surface separating regions that are very highly ionized, being ionized repeatedly by ionizing radiation, even while electrons are recombining continuously with nuclei. They're being reionized and recombine and ionized and recombine. And on the ionized side of the ionization front, they stay highly ionized. But there is a surface beyond which the ionizing radiation has not yet reached at any given moment, at any given slice of the universe. And on the neutral side, there is essentially no ionizing radiation and no photoionization yet. And that surface that separates the two regions is called an ionization front. And there is a very fortunate property for study of reionization, which made those N-body and radiative transfer post-processing simulations so productive for so many years prior to this era of radiation hydrodynamics. And that is that the speed of the ionization fronts is highly supersonic, even compared to the sound speed of the photoionized gas. So photoionized gas has a sound speed of order tens of kilometers per second. And the ionization fronts that sweep across the intergalactic medium ionizing the universe travel at thousands of kilometers per second. And in some cases, when the sources are bright enough and they first turn on, the radiation streams out at nearly the speed of light. The radiation is traveling at the speed of light. The ionization front, they drive into the neutral gas, can approach the speed of light. And in that case, the time for changes to occur in the gas is the time for the ionization fronts to transform it. And that is the light crossing time. So in order for us to break up a simulation into enough finite difference times to accurately track the evolution over time, if we were doing only gravity and galaxy formation, gas dynamics, which are challenging enough, we would need hundreds or thousands of times fewer time steps than we need when we add the ionization fronts and the radiative transfer. Well, I can tell you, to solve this problem with hydrodynamics and gravitational dynamics and radiative transfer, and to do 100 to 1,000 times more time steps than we are used to doing, even for our best galaxy formation simulations of volumes this large, is completely out of reach in the conventional approach. But with the invention of the GPU, CPU hybrid computers, this became possible. And so Dominique Aubert re-engineered the Aton code he developed with Tessier and the Ramses code, put them together in such a way that the Ramses code sits on the CPU of a massively paralleled supercomputer, each node of which has one or more GPUs, and the GPUs are doing the radiative transfer and the ionization rate equations much faster, so that they can do essentially 100 time steps of radiative transfer and ionization balance for every hydrodynamic and gravity time, which is lumbering along on the world's fastest massively paralleled CPUs. So I don't have more time to tell you about that, but we've gone through a few generations now of simulations. It was necessary for us to have access to the world's leading hybrid CPU GPU computer to do this, which at the time of the simulations of most of my results will be the Titan supercomputer at Oak Ridge, which we were fortunate to have access to in multiple go rounds, and which we are now just starting the third generation, CoDa 3, on the replacement for Titan, which is something I will have to tell you about in the future. There's also an AMR version of this code, which we've used to simulate, and I don't have time to tell you more about that. So I can see my time is going to run out before I've given you even my first results. So I really have to be selective and pick and choose now. Just to give you the sense of it though, when we run the N-body simulation without the radiative transfer and the gas dynamics all the way down to redshift 0 from these constrained local universe in simulation initial conditions produced for us by our collaborators in what is called the CLUES Consortium, based upon galaxy redshift surveys of the local universe, and essentially producing initial conditions that when run forward in time will reproduce what we observe. On the right is the N-body simulations of a certain inner portion of the volume we simulate, and on the left are data of the local universe. So let me tell you, I'm going to tell you about results that are primarily coming from CoDa 2.
Can I ask a question?
You can, but I have to be very mindful of the time since I've run past my clock. Go ahead.
Well, just a quick question. So the minimum helium mass is coming from where in your simulation?
The minimum halo mass in my simulation will be dictated by the particle mass resolution, which is given by the fact that even though we've done this hero thing, we're still limited to having 69 billion n-body particles, which is 4,096 cube particles in a volume of order 100 megaparsecs. And that means that if we believe that we can identify a galactic halo if it has a few hundred particles in our n-body simulation, that corresponds to 10 to the 8th solar masses. Does that answer you?
Yes, thanks. Thanks a lot.
Good. Okay. The new simulation, CoDa 3, which is just underway, will improve this by a factor of 8 by doing 8,192 cube. But this is the limit. That's the next talk. When I return, I'll give you that talk. Okay. So just to give you an impression, though, about how highly resolved this is, with this extent being 100 megaparsecs in the vertical direction here, you can't really appreciate the fine structure until you zoom in on that image. And if I zoom in one more time, you can see I'm finally beginning to see the cosmic web, individual galaxies. Each of these is a galaxy or galactic halo, but it's also a galaxy. And the red patch corresponds to a galaxy that has a starburst underway that also is blowing out super bubbles as well as ionizing. The blue region is ionized by, now this is bad. Okay. The blue region is the photoionized region. The boundary between them is the ionization front. And you can see it's a patchy process that starts around the galaxies that are formed at the intersections of the filaments of the cosmic web and propagates away into the lesser and later to form structures. So just to convince you that the CoDa 2 simulation satisfies in our choice of the properties that go into making sure that galaxies form stars and that the stars have ionizing radiation, which we transfer out of the galaxy, but we do not have the resolution necessary to resolve the interstellar medium of each individual galaxy. So we must decide on a subgrid criterion to suggest that the properties we cannot resolve in each individual cell inside a galaxy would have triggered star formation. And then we allow that star formation to be a source of ionizing emissivity, but we then transfer it out of the cell, between cells and across the universe. So then when we're done, we have to hope that our choice of that efficiency for forming stars, which we don't tweak during the simulation, was sufficient to reproduce the observed universe, and not only that, but produced a host of observable constraints. So we found good agreement in the end of reionization and in satisfying the Planck polarization observations, and I will not say more about that. Let me, one detail, if I had time to come back to it. There is however, a small overshooting of the UV ionizing background left when reionization is over, compared to what we would have liked for the Lyman alpha forest observations in the post-reionization universe. And that is consistent with having a somewhat lower neutral fraction as the relic left behind after reionization. And I have an idea for that, which if I get to it, I will tell you about in the last part of the talk. One of the most important observables these days, as we push the boundary back in time to reveal the presence of high redshift galaxies, not just quasars, but galaxies which are emitting as star-forming galaxies, whose UV continuum luminosity escapes from the galaxy below the Lyman edge of the hydrogen in the galaxy that would shield us from seeing it. And so this is the radiation that isn't the ionizing radiation, but gets out and makes its way all the way for us to observe it as the UV luminosity function of galaxies of high redshift. And what I want you to see from this plot is that at all of the redshifts 6, 7, 8, and 10 plotted where the observed points are plotted along with the average luminosity function from the CoDa 2 simulation, they are in good agreement, and I won't say more about that. However, one of the interesting outcomes of a simulation like this is to show us that when the observations are capable of doing more, they will see that the UV luminosity function of high redshift galaxies is itself inhomogeneous in time and space. And for anyone to plot one luminosity function as is plotted on this plot as the average for the universe is premature for the observations. They have not sampled the average universe as even the volume large as we have in our simulation. And to demonstrate how inhomogeneous it is, I'll just show you the box undergoing reionization. And you will see that the sources of the reionization inside the blue regions are not at all homogeneous in time and space. So why should we expect the luminosity function? Here we have the galaxies superposed on a map, not a map of the cosmic web, and not a slice of time showing the ionized regions, but a different kind of map, which is the reionization redshift field. It looks like the cosmic web, doesn't it? And they do resemble each other because the patches that get ionized first are the patches that are where the sources are clustered and form first. So of course they're correlated with each other. Halo clustering correlates with reionization redshift. And here the earliest places to reionize are the lightest color and the darkest are the last to reionize.
Well, that's 45 minutes.
Thank you. I asked you to tell me, and I wanted to know. I am going to keep going, and I hope I don't insult you if I go all the way to the 60-minute, but I can stop earlier if you would like. You let me know. So what I wanted to show you here, and then I will not dwell on this further, I'll go on to the next topic, is that indeed the luminosity function of high redshift galaxies is itself very inhomogeneous. Take redshift 6. If we observe a patch of the universe which reionized at a redshift before 9, the luminosity function is much higher. And the rise, this is the bright end. This is astronomer notation for high luminosity on the right and low luminosity on the left. In the UV continuum. Not surprisingly, the brightest objects are fewer, so the luminosity function tails off as you get to the bright end. But despite the fact that there are more and more lower luminosity galactic halos, their luminosity function also flattens, and it flattens because they are subject to the reionization feedback that deprives them of the gas to make star formation. So why the luminosity function is inhomogeneous during reionization? Well, the star formation rate depends upon halo mass, and the halo mass function is inhomogeneous. Let's talk about that first. Here I plot the star formation rate as a function of the halo mass. And over a large range of masses, it's actually not badly fit by a power law. The mass of the halo raised to the 1.4 power shows that higher mass halos form stars much more efficiently. However, below about 10 to the 9th solar masses, you see that when reionization overtook the local halos, they were deprived of further fuel for star formation, and their natural tendency to join that law is defeated, and their star formation rate is suppressed. However, the mass function itself, even for the things that are high mass and are immune to that suppression, is different in regions that ionize early or late. So you can see where the reionization redshift was greater than 9, the abundance of halos of all masses was higher than for the region that reionized the universe at less than 7, even though these are plotted at the same time. The next factor is that star formation rate depends upon halo mass, and reionization suppresses star formation in the low mass halos, as I said, but also reionization is itself inhomogeneous. And that's important because the second line I've told you about, the third line, reionization is inhomogeneous. I have to explain why that's another factor. Well, this is the global effect of reionization, averaged over the whole volume. But if I look locally, I find that the local reionization is what determines when the low mass galaxies will be deprived of their supply for star formation. And if they form before their neighborhood is reionized, they're not deprived. If they find themselves in a part of the universe that reionized early, they are suppressed early. If they are in a part of the universe that ionized late, they are suppressed late. And one must take that into account as well. So we do that. And here again is this local reionization redshift field. We thereby show that indeed suppression is a local phenomenon. Low mass halos, which are the ones that are suppressed, wait until their neighborhood. If you look on the left panel, the 2 dots tell you when each of these curves was in a region where the redshift of reionization was reached. Between the 2 dots, that's the redshift of reionization. And as you can see, each region, even the low mass halos, continued forming stars in those regions without suppression until their neighborhood was ionized, and then down it went, the rate of star formation in the suppressible halos. On the other hand, halos more massive, not suppressible, continued to form stars even after their neighborhood was ionized. And then lastly, the star formation rate for all halos actually seems to know about its local reionization redshift. Now, this is the most astonishing thing. Everything else I expected, but I did not expect this. I did not expect that if I took a halo, which was so massive, that in effect, it could care less about the photoheating of the intergalactic medium around it. Its gravitational potential well was going to be strong enough to pull that gas in and force it to make stars if it so chose. So what I didn't expect was that if I found such a massive object in a patch of the universe that was the earliest to reionize, that it continued, not only did it form stars at a higher rate than a patch where the same halo mass was forming at a lower rate, but it also continued to be the dominant leading star formation rate in the universe, even after the whole universe was reionized. Okay, which galaxies dominated reionization? I wouldn't finish my story if I didn't tell you that. Well, this depends upon three things. We've talked about the star formation rate versus halo mass. We've talked about the halo mass function. But we haven't talked about what fraction of the ionizing photons can escape from the halo. And that makes all the difference. Well, this required that we take the results of the CoDa 2 simulation and make a catalog of all of the galactic halos, and then recalculate with a different radiative transfer method, which is ray tracing, the path taken by all of the ionizing radiation released inside each galaxy until it escaped from the galaxy to determine what fraction were able to escape. That, I won't tell you technically more about how we did that, but the answer was that the escape fraction, not surprising, is higher for low mass halos and decreases with increasing halo mass. So it's almost 1 for the lowest mass halos, and in this plot by the end of reionization, not at the beginning of reionization. For a given halo mass, the escape fraction increases over time. And then there's a significant scatter in the escape fraction about the mean relationship versus halo mass, even at the same redshift, a scatter which is greater at low mass. And what we need to determine what dominated reionization is the product of that escape fraction times the star formation rate for an individual halo. And where we now realize that higher escape fractions at low mass offset the higher star formation rate at higher mass. Did someone speak? Sorry. So we fold that in with the halo mass function, and the halo mass range that dominates the total rate of photon release is lower than the mass range that dominates the total star formation rate density, since the escape fraction is lower for higher mass halos. And when the universe was a half ionized at a redshift of 7, 80% of the ionizing photons released came from halos between 1 billion and 40 billion solar masses. So we need to make sure we ask the question, what dominated reionization when, not just overall, because when the universe was only 10% ionized at a redshift of 8.5, 80% of the photons at that time came from the halos least able to survive the feedback effects with a mass less than 5 × 10⁹ solar masses. Now, if I said to you, how did that compare to the galaxies that we observe in that halo mass function? Well, it turns out that the galaxies that dominate reionization between a redshift of 6 and 8 would be observed in the luminosity function to have the luminosity between -13 and -18. And we know that deep surveys in cluster fields have not yet probed this very well, but they may soon detect the galaxies responsible for more than 80% of the reionization photons at redshift between 6 and 8. Something I won't tell you about, but I'll just advertise, is that we did, after all, promise to tell you about the ionization of the local group. And we have done that. And the only highlight that you can get from this figure is that it is a plot of the ionization field zoomed in to the local group. And you might think that I'm showing you the local group itself and the Milky Way MW and Andromeda M31. But what I'm showing you is that the redshift of reionization of the two were comparable, and according to the color table, they were sometime around redshift between 10 and 11 in the center, but extending over 500 million years all the way down to redshift 8.5. But you'll notice there's no bridge between them. And in a reionization map, to create islands in the map surrounded by volume, which is at a lower redshift of reionization is to show that there was no propagation of reionization effect from one island over across the sea to the other. So that's why we call these islands in the stream, because this means that not only was the Milky Way and M31 not externally ionized by objects as far away as the Virgo cluster, as one might have guessed, but they also ionized their own local volume and did not wait for each other to ionize the other. Okay, and I'm going to run out of time very quickly, so let me get down to a last. I'll talk about two last highlights. One involves a new kind of radiation hydrodynamics, which involved taking the Gadget smooth particle hydrodynamics code and adding a radiative transfer algorithm to it, which was the PhD thesis of my student Hyunwei Park. And when we did this, we were able to simulate that unresolvable level of, here we are, the unresolved level that the CoDa simulation would have fit inside a few cells of the CoDa simulation. So here we only have a few hundred kiloparsecs across, but what it shows is that the scale of the cosmic web continues all the way down to the mini halo scale, unresolved by those simulations. And when they are exposed to ionizing radiation, the gas in those systems photoevaporates, and the letter C stands for the clumping factor of the ionized gas. The mean square density, which enters the recombination rate. So as long as that number is higher than 1, this says that the replacement of all that inhomogeneous gas with an average density would underestimate its rate of consuming ionizing photons. And that's an important element in the proper description of reionization. And it has an observable consequence. That effect can in fact vary on large scales, because there's another effect that affects the cosmic web on small scales, which is that coming through the recombination of the universe and the decoupling of the photons in the microwave background from the atomic gas, left behind a relative supersonic drift velocity between baryons and dark matter, which redshifted away for the most part, so that simulations like the CoDa simulation don't need to see it because they couldn't on the scale of their resolution. But on the scale of the simulations I just showed you the movie of, that drift velocity makes some patches that have a large drift velocity capture baryons into the halos less efficiently than where the drift velocity is small, and this effect can actually be correlated on very large scales on the size of the box I showed you in the CoDa simulation. And that's important because observers are telling us that there are very large fluctuations when reionization ends in the quasar absorption line transmission that I first showed you in the beginning of my talk. And it's a challenge to explain it. So one of our hopes is that this large scale variation in the reionization caused by a variation on large scales in how quickly a given box like the CoDa simulation will reach the end of reionization can explain the large scale variation in the relic H2 opacity after reionization ends and is observed in the Lyman alpha forest. And then finally, the last thing I will say is that the small scale of the mini halos can also be a source of radiation that not only consumes, not only are the mini halos and their filaments consumers of ionizing photons as they're being evaporated away during reionization, but since they form first and then merge into the atomic cooling halos later, they actually are capable, if they can form stars before they're suppressed, of getting reionization started early. And we predicted in our N-body plus radiative transfer simulations back before the Planck satellite released its first data, that this effect would actually produce a tail that would ionize the universe to the first 10%, well before the atomic cooling halos would ionize the remaining 90%. And we predicted that the Planck polarization and isotropy would actually be able to detect that, and in so doing might be the first ability to detect the first stars forming inside mini halos as what are called population 3 stars at the beginning of reionization.
That's it, Paul, I'm afraid that you've reached.
Okay, so my punchline is the following. We have now taken the results of Planck at the end of the life of Planck. That was a prediction. We've now taken the Planck legacy data and shown, and this is my last transparency, that early onset self-regulated reionization with mini halos agrees well with the Planck E-mode polarization data, even with that substantial tail of high redshift ionization, which was not considered by the Planck collaboration in making their conclusion and is therefore beyond the limit proposed by the Planck collaboration publications. And I'll stop there. Thank you.
Thank you very much for that nice and wide-ranging talk. It is over the hour now. Are there any questions for Professor Shapiro?
Hey, David, I have a quick question. Paul, you mentioned the missing satellite problem. Did you have something concrete to say on that?
Yes. From the point of view of the suppressible halos in the, well, let me actually show it. I'll show it in reference to this last plot. If you look at the ionization rate plot, you will see 3 types of halos shown there. And when the CoDa simulation simulated, we didn't have mini halos, but we had the LMOX and the HMOX. And you'll notice if you focus on the dash curve, the LMOX are below a few times 10 to the 9 solar masses, and the HMOX are above that. And you'll notice that the contribution of continuing star formation by the even more abundant low mass halos shuts off because of the reionization feedback. So the answer to your question is that the great majority of those dwarf satellites are indeed left dark by reionization.
Okay,
and
thanks.
I won't say more than that now.
Okay, if anybody else has any quick questions, we could take them.
May I have some live questions? Okay, so you showed the local galaxy numerical simulation data where we can see the Milky Way and the Andromeda galaxy and etc. What is the initial time and what is the initial condition? Could you explain a little bit more? So when you numerically simulate, each particle means what? So the initial condition is what I'd like to ask.
Okay, so the initial conditions are a realization of Gaussian random noise in the cold dark matter model, just like any that you would have used in other galaxy formation simulations.
At
or
what time, in terms
with
of Z? Okay.
Sorry, but with a twist. So
Okay.
I want to answer you by telling you what the twist was. The twist is given to us by this CLUES consortium. And so I have to tell you what the CLUES consortium does to generate those initial conditions. They take the data for the local universe within a few hundred megaparsecs of the Milky Way, for the redshift and peculiar redshift and distance to galaxies. And this is in the nonlinear universe today. They then, and I won't go into detail because I don't think you want that, but I can give you more detail if you'd like. But they then essentially reverse engineer that to determine what linear amplitude initial perturbations at high redshift would have to be in order for them not only to be Gaussian random realization, but it's as if you were able to roll the dice countless times, each one producing another Gaussian random realization, but you sifted through those outcomes until you got one that reproduced the observations of the galaxies and their peculiar motions in the universe today.
Okay, so to put my question in a different phrase, so local group and the other galaxy clusters will may look like somewhat different. Then what is the specific things that is implemented in the initial condition to reproduce present local group picture? Does it make sense?
Yes. Okay. I thought I answered you, but I didn't give you enough for you to get it. So you for example, for example, or you may know what is called the Zeldovich approximation, which is a method for moving mass points dynamically as they would move under the action of their mutual gravity in the expanding universe, but to do it with an approximation that assumes the accelerations of particles are fixed in time by linear perturbation theory, but to propagate it forward into a nonlinear regime. And there's a whole industry devoted to how well it works and on what scale you need to filter the final answer in order to know that it worked. And anyway, machinery like that goes into the reverse engineering that I was telling you about. But in the end, in order to see objects that I would actually call the Milky Way and the M31, what I'm saying is an object at the right location, with about the right mass, with about the right size in the dark matter halo. And the machinery that reverse engineered the initial conditions, the data is not available for reverse engineering deep into the nonlinear regime inside the formation of a galaxy. So you're talking about some filtered scale, which is too large to literally pick out the Milky Way and M31 as neighbors. So what you do then is you take the outcome of the reverse engineering, and then you run literally hundreds and hundreds of n-body simulations with higher resolution Poisson noise added, and you sift through them, throwing away the ones that don't look like the local universe. You keep throwing them away and throwing them away and throwing them away until you get the ones that have a Milky Way, an M31, the separation between them right, the mass right, the size right, Virgo in the right location with the right mass, and so on. Does that answer you?
Okay, thank you very much. I have much better understanding. Thank you.
Good.
Thank you very much for those questions and those responses, Paul. I think we're going to have to draw it to a close at this point. So I'd just like to thank you again for taking the time out of your evening to speak to us.
My pleasure.
And yeah, and on behalf of the other members of the organizing committee and the Korean community in general, which I think benefited from that talk then. It is I'd like to, yeah, so thank you again.
You know, I didn't ask you whether it was being recorded.
No, we haven't. Owen, can you double check?
So it is being recorded, but whether or not we upload it depends on you, Paul, right? So if you're happy with the talk and you're happy that we put it on the website so people can see it. And,
I think the only, normally I would just say yes, but experience tells me if you can you, because I've been teaching online, and so I know that that's the way it works when you teach online, is you are given a chance to see it before you so-called publish it. Is it possible for me to?
yeah, we can send you a copy. So basically, we'll send you a private copy. Everything gets uploaded to YouTube, so you'll have some password, have a look at it, and then you can give us permission later. You can make a decision later, right?
Okay, good. And since it's a recording, it will show my slides, and the fact that I have slides in my talk that aren't shown has no significance, right? The recording just sees what you see.
Yeah, whatever you showed us today, right?
Yeah, that's fine.
Okay.
Good.
Okay,
No,
so
therefore, I will just, you send it, I'll look at it just to be sure before I say yes.
Okay, no problem. Right.
Great.
Okay.
Thank you very much.
No, thank you very much. It was very interesting. Thank you.
Thank you. And goodbye to all my friends. Take care. Bye-bye.
Thanks.
Bye-bye.
Bye for now.
Bye.